This is the Polyprocessing Tech Talk podcast on PFAS. Joining us today is Bob Molitsky, our Midwest Regional Sales Manager, and a special guest, Katie Wolohan with Barr Engineering. Welcome, Katie.
Thank you. Thanks for having me.
You bet. Bob, good morning.
Good morning, Marshall. Good morning, Katie. Good to be here.
Katie, can you tell us a little bit about you and your company, Barr Engineering?
Sure. I'm Katie Wolohan. I've been at Barr Engineering for a little over 7 years now. I'm a professional environmental engineer. I work mostly on water and wastewater treatment and water reuse projects, treatment system design, feasibility studies, bench and pilot testing, all things water. Whatever needs to get out of the water, I try to get it out. Barr Engineering is a environmental consulting firm. We're based out of Minneapolis, Minnesota, is where our headquarters are, but we have 10 offices across the U.S. and Canada. We have about just under 800 engineers and scientists, so kind of a big little guy in the consulting world. And we have 4 business units: engineering design, assessment and remediation, water resources, and environmental management. And I'm in the assessment and remediation business unit in the water and wastewater engineering practice group. So we really do a wide range of services, everything from windmill-based design to environmental permitting compliance. We have a stack testing group, a lot of hydrogeology, groundwater modeling, and then, of course, water and wastewater treatment.
Can you give our listeners a little overview of PFAS and how it is used?
PFAS stands for per and polyfluoroalkyl substances, and a few years ago, a more common acronym was PFCs, or perfluorinated chemicals. And the best way to explain why we moved to PFAS instead of PFCs is all PFAS are PFCs, but not all PFCs are PFAS. So the EPA moved towards calling these substances PFAS, or PFAS, as we like to say. PFAS are synthetic, man-made chemicals, and as you mentioned, they include more than 4,000 individual compounds. They serve many really useful functions across a variety of industries. They're used to coat nonstick cookware. We associate PFAS to Teflon. They're used to make surfaces waterproof or stain or grease resistant, so things like carpet, mattresses, food packaging. They're used in a lot of clothing products, so Gore-Tex, Nomex, a lot of things that we like to wear to protect us from the rain, shoes that are waterproof or water resistant. And so PFAS are usually found in a liquid dispersion or a formulated mixture that are then used to coat the surface of something. So whether that's clothes or a consumer product. They're also used in aqueous film forming foam, or AFFF, or firefighting foam, which is used mostly to put out Class B fires, which are fuel-based fires. They create a coat basically between the fire and the oxygen source to help extinguish fire, so very useful for that. And they're also used in the automotive industry, building construction, electronics industries, aerospace. And we call PFAS emerging contaminants, which means there's been some studies done that have identified risks associated with human health and the environment, but they're still learning more about what that actually means. So we call them an emerging contaminant.
Katie, it sounds like these compounds are all around us, obviously, in almost everything we do daily. How do they find their way into our drinking water?
So there are a few different ways that PFAS can enter into drinking water supplies. When drinking water source is groundwater, so if that's a municipal supply or a private well, PFAS usually enters the groundwater by traveling through the unsaturated soil zone. So it ends up on the ground somehow, and it can get there through a few mechanisms. So either that might be a historic spill or a disposal site, but oftentimes PFAS gets there through air deposition. So some industries that manufacture or use PFAS in their process, they have stacks that control air emissions, and PFAS can become airborne and travel great distances by air before eventually landing somewhere on the ground. And then, of course, it takes time for the PFAS that's landed on the ground to make its way to the groundwater table, but over time it will get there, usually through flushing from atmospheric rain and other water events that allow it to make its way down to the groundwater. PFAS are also found in many landfills. So landfills obviously accept a wide range of waste, and a lot of consumer waste, manufacturing waste, industrial waste does have PFAS in it. And landfills, at landfills, PFAS will report to the leachate, which in a lined landfill, this leachate is typically sent to a wastewater treatment facility. And usually the wastewater treatment facility doesn't have a means to treat PFAS from wastewater. So then it can get back to the drinking water source through that mechanism too, because treated wastewater is discharged to surface waters that can be drinking water sources or that eventually infiltrate back into the ground and can be a groundwater drinking water source. And wastewater treatment facilities have biosolids as part of the process, and biosolids are usually dried and then land applied. So a lot of farmers take them, and through land application, PFAS in biosolids can also make its way back into the soil, back into the groundwater. So a few different ways PFAS will report to water one way or another.
Katie, what makes PFAS unique and challenging to treat?
Yeah, so PFAS are very persistent. They don't break down, they don't degrade, they get hung up on organic carbon in soils, they get hung up on surfaces of things, they're very sticky. And they're also not destroyed by common water treatment methods and technologies. So a lot of other emerging contaminants, pharmaceuticals, there are pretty well understood treatment technologies that can remove them from water but can also destroy them. And what is difficult for PFAS is because of the bond they have, the carbon-fluorine bond, it's the strongest bond in nature, it's very difficult to break. So that leaves pretty limited options for PFAS water treatment. And what we're seeing commonly used now are adsorption processes, where PFAS is absorbed onto some type of media that eventually needs to be incinerated to actually completely destroy the PFAS. So PFAS start to break down into smaller chains at approximately 300 degrees Celsius, but complete destruction occurs at about 950 degrees Celsius. So it's a pretty significant amount of energy needed to actually break the bond and destroy the PFAS. So that's hard to accomplish in a treatment process. So like I said, mostly we're seeing media absorption, and then that media ultimately needs to be incinerated. There are some experimental technologies out there that are really at the very, very base level, bench scale type tests, like electrocoagulation, other like plasma reactions that could destroy PFAS, but they're still a pretty far ways away from being viable treatment technologies. And once they are viable, it'll probably be better for pretty small volumes of water. So treating a drinking water supply with that type of technology will be probably not feasible for quite some time, if at all. So those are a few ways that make it quite challenging to treat.
What currently is available to treat water? What is your company working on that's out in the field right now? And what volumes are we talking about that we're able to treat at this point?
Yeah, so right now, probably the best understood technology or treatment method is using granular activated carbon, or GAC, GAC. And this has been used for a while now for PFAS adsorption. So you have usually a vessel system where you have at least two vessels, usually a lead and a lag vessel. The water enters one vessel, the PFAS absorbs onto the carbon, so it kind of wiggles its way into the pores of the carbon granules and just sticks there. And at some point, it can't take on any more. It doesn't have any more absorption sites, and it's considered spent. And at that point, you would remove the carbon from the vessel and send it off for incineration. That's the most common disposal method now. It's usually what people feel most comfortable with because, as we talked about with the landfills, there's not a lot of other options for disposing of this media now because it's not a permanent and forever hold. Granular activated carbon can release PFAS at some point, and we actually see that as it starts to get spent and has no more absorption sites, it will start releasing some PFAS, including mostly the shorter chain PFAS compounds. So granular activated carbon is one, and then kind of coming up close behind it and also being pretty widely used is ion exchange resins. And there are two types of ion exchange. There's regenerable ion exchange and then single pass ion exchange. And the way ion exchange works, it's media absorption similar to the granular activated carbon. However, it's a little more scientific. The resin is engineered to say, hey, I'll trade you this chloride ion or some other type of inert ion for the PFAS. So as the water passes through, this ion exchange happens and the PFAS gets stuck onto the ion exchange resin. And ion exchange resin on a per pound or square foot volume basis is more expensive than carbon quite significantly. However, it requires a shorter empty bed contact time. So granular activated carbon requires about usually we recommend 8 to 10 minutes. If the PFAS concentrations are really high, sometimes we have a much higher empty bed contact time. And what that refers to is the amount of time that the water is in contact with the media. So from the time the first drop hits at the top of the vessel to when it exits the bottom, it was in there for 10 minutes if it had an empty bed contact time. And ion exchange typically requires a shorter empty bed contact time, so around the order of like 2 to 4 or 5 minutes, depending on the concentration. So that means you can have a smaller vessel with a smaller volume of media to treat the same flow rate. And the types of flow rates we're treating, we've designed some really tiny systems that are treating on a batch treatment process basis. We have helped with point of entry treatment systems, so just home systems that treat as low as 8 gallons per minute, or a business system that treats 30 gallons per minute, so some really tiny media absorption type systems. And then it looks the same on a much larger scale. So some of our industrial clients that are implementing PFAS treatment, they'll be treating 500 gallons per minute from a wastewater treatment plant, or a drinking water supply where we're designing a treatment system to treat up to 2,500 gallons per minute. So they can get pretty big, but it all just kind of scales up. So even the home systems would have a lead and a lag media vessel. They'd be small, like probably the same size as I am. And then in the industrial applications, they're much larger, very tall, very wide media absorption vessels. And then we get asked a lot about membrane treatment, ion exchange, nanofiltration and reverse osmosis. And these technologies are effective for PFAS removal. We're not seeing them employed as widely because they come with a pretty high operations and maintenance cost, capital cost, and there is a concentrate stream that's produced. So you're essentially concentrating the PFAS into a smaller volume. You're pushing water through a membrane, some water stays behind as concentrate. That's where all of the things you were trying to remove remain. And then you still need to then do something with that. And being a liquid stream, it's more difficult to incinerate that and quite costly. So there's some other type of treatment then that would be needed. And by concentrating everything up, it's making it a little bit more difficult to treat then with media. It's not impossible, so depending on the water quality, it is possible then to send the concentrate to a media vessel, but it's a little more challenging. And in the Midwest, in Minnesota in particular, where I am, we have a hard time with membrane treatment technologies because we really have very limited options for disposal of concentrate. So even when we consider it for non-PFAS applications, when you have that concentrated stream that's high in salts, high in TDS, high in metals, it's hard to find a place to put that, to treat it, or we don't have options for injection, or we don't have an ocean to discharge to, so it makes it difficult to treat with membranes.
So Katie, you talked about storage vessels or lead and lag vessels, or so you talked to them being very small for smaller systems. So is that where chemical storage tanks are normally used in the system, our traditional chemical storage tanks?
Mostly we are using pressure vessels for the media absorption piece of it. We have a client who has a pretty difficult to treat, relatively small volume wastewater treatment stream, and historically they have sent this to the sanitary sewer district, and last year they proactively sought to treat PFAS from this wastewater in order to be able to continue to discharge the sanitary sewer and remove that PFAS mass from the loop. So we designed a batch treatment process that can remove high solids, total organic carbon, and other contaminants from the wastewater before it's even treated for PFAS, and that's where we're using polyprocessing tanks, the sloped bottom vertical tanks to store untreated and treated wastewater. And then we're also using polyprocessing cone bottom reactor tanks for the pre-treatment piece of the process. So ahead of designing this treatment system, we completed bench and pilot testing to understand how we could actually treat the wastewater and how we could remove the solids, total organic carbon, and other things from the water that would make it harder to treat in the pressure vessels for PFAS removal. And so we came up with a pH adjustment coagulation process that's used to drop out the solids. And so that process, that pre-treatment piece, is all happening in the cone bottom reactor tank before the water is decanted off and sent through the high pressure media vessel.
So it sounds like the treatment is a multi-stage process where just using high pressure filtration could create a consolidated waste stream, but that's not really the answer.
Yeah, so it's kind of the catch-22, because if you just if you didn't use membranes and you sent that water through conventional media absorption, so the granular activated carbon or the ion exchange, as I mentioned, you're treating a larger flow rate and the PFAS is still absorbing onto the media. However, if you're using reverse osmosis and you're treating the water that way, you have this then concentrated stream, and let's say it's 20% of that volume you were originally treating. So you have a much smaller volume to deal with, but the wastewater, or that concentrate stream, it has a lot of concentrated things in it that would make it difficult to absorb onto media. Media would then have to choose, like, am I going to absorb the PFAS, or am I going to absorb total organic carbon, or iron, whatever has been concentrated up. It'll compete with the PFAS for absorption sites. So it's sometimes that concentrate then would need to be further treated before you could use conventional media absorption. And I think that in the future, there will be options that you could send that smaller volume concentrate stream from reverse osmosis or another membrane technology. You could send that to some type of electrochemical, electrocoagulation type destruction system, but we're just not there yet. So once you have this concentrated stream, really the options are to reabsorb it onto media. So you're still ending up with some type of media absorption element.
That's great, Katie. It really sounds like Barr Engineering is kind of leading the way, at least from what we're seeing in this in PFAS removal. If one of our customers wanted to contact somebody at Barr Engineering, who would that be, as far as looking into your services?
Yeah, they're welcome to contact me. If you Google Barr, B-A-R-R, PFAS, you'll hit our landing page, and you can learn more about our service offerings in general and about our PFAS services. We have an emerging contaminant landing page, and we're helping clients with a wide variety of things. So just even very preliminary, helping to identify potential risks, just sitting down to have a conversation about PFAS, all the way up to helping our clients with remedial investigations, feasibility studies, fate and transport modeling, a wide range of things. So on that same page, you'll be able to see our experts in our PFAS services, everything from chemistry, stack testing, and air modeling, groundwater modeling, water treatment, and everything else. So, and there's contact information for everybody there as well on that page.